right, before we start, I have a question. I know the homework is due tomorrow. Are you working on it? What's the situation? Nick, you are the barometer of the class, because you always do things the last minute. So we're okay on schedule? Yeah, should be. There's a lot of uncertainty there. So what's the idea here? Right, I get no response. You know what? No response means the homework is here tomorrow, and there will be a new homework on Thursday. All right. So what we need to do is, we're covering sort of general algorithms for inference, and in particular, we were talking about the SumProduct algorithm in trees, which is applicable both for directed and undirected trees. And so we will summarize this today, give you the algorithm. Hopefully there will be a programming homework on this topic for next week. And also we'll generalize this with polytrees by introducing what is called factor trees. Okay? And I think depending how far we go today, on Thursday, we're going to start talking about the junction tree algorithm, which is even more general. And after that, actually, we're going to start doing lots of application examples. So some of the things that we have seen briefly, we will see them again in detail, including hidden Markov models, state space models, etc. But it's better to see the general theory and then go to specifics rather than the other way around, and then say, sorry, we ran out of time. There is no room for the general algorithms. Okay. So we were looking at trees, all right, and we discussed if you have a directed graph, you transform it to an undirected graph, and so we discussed about the SumProduct algorithm for a tree, okay? And the whole algorithm is what you see on the first box, all right? So you have to introduce the evidence, and the way you do this is by modifying the node potentials, all right? So if xi is fixed somewhere, and you already have a potential psi xi, you multiply by delta function to force xi to take this value xi bar. In many ways, if you don't have these self-potentials, this is still useful to impose evidence, basically, in your graph. All right, you have to choose a root in the graph, and in some sense, for now, you can take anything you want to, because this is a tree. So any node, you choose a root. And the algorithm starts with very simple steps that require sort of recursive programming, okay? So you start with a node in the neighborhood of the root, and you call this command collect f comma e. Okay. So the collect algorithm you see basically here, right? So if you have messages, if you know the message from k to j and from this node to j, then effectively you're ready to propagate messages to node I. And these messages are given by this command that you see here. You multiply the potential on I and j, the self-potential on j, and all the incoming messages that are functions of xj, and then you marginalize xj. So the passing message, basically, it's a message that depends only on xi. Okay? So in the collect stage, basically, you need to be able to start propagating this message from, let's say if this is the root, all right? To be able to compute these messages, you need to compute the messages coming from their children. And then to compute those messages, you have to keep going down. Eventually, this will take you down to the leaves. And that's why the collect algorithm, you notice, it's a recursive algorithm. So you start from the root, and then you go one step down at a time until basically you're at the bottom and you can already start collecting messages. Okay? So you don't have to write any fantastic algorithm. This is the whole algorithm basically for collecting the messages. To be able to send a message from J to I, you need to have all the incoming messages arriving in node J. Okay? So this is the collect. And similarly, the distributed messaging algorithm, you can see here, if let's say all the messages arrive at the root, then you are ready to start sending messages from the root down to the children of the root, all the way down to the leaves. So if you can send this message, and then the distributed algorithm is basically to propagate it. And again, the propagating of messages follows exactly the same command that, if the messages go up or down, it's basically the same command that you see here. Okay? So the only thing you have to keep in mind when you propagate message from J to I, and you account, let's say, for the incoming message to J, you don't account for the message coming from I. So you're not going to send to I the message I sent you. Okay? This is fundamental to this message passing algorithms. So eventually, the collect step, basically you go all the way down until you start sending messages to the root, and then from the root you go all the way down to the leaf sending messages. So in every edge, at the end of the day, you're going to have messages in both directions. Okay? And we already have proved this for trees. If you have this message and you want, let's say, to compute the marginal of a given node, the only thing you have to do is multiply all the messages arriving to that node times the potential of that node, then normalize. Okay? So, and we already discussed, if you want, let's say, the joint distribution of I and J, you can sort of write a similar algorithm with what we derive for chains. Okay. So again, you choose any root, you send messages from the leaves to the root, and then from the root down to the leaves, and then that's it. I mentioned that, so this algorithm is basically for trees. If you try to generalize this, in principle it may work, right? So even if you don't have a tree and you try to use the same idea, you call something the root and you start sending messages, you hold it and at one point you say that's the root, and you send messages from the leaves all the way up and the other way around. This may work even if you have loops, okay? But there are no guarantees that actually will work, okay? And there are versions of this algorithm, including what is called loopy belief propagation, that basically at the end of the day do the same message passing in some systematic manner, and then because this algorithm may keep going forever, you just stop it at a certain time when the messages don't change very much, and you call that the end of the story, hoping for the best. Okay? Many years ago, when we were writing a proposal, somehow I got excited about this concept of loopy belief propagation, and I told all these mathematicians, so we have to use this loopy belief algorithm, and everybody had no idea what I was talking, because loopy means crazy, okay? But obviously here, it's not that it's crazy, it means there are loops, okay? But it's all relative. The algorithm may go crazy if you have loops, all right? So one way you see it, or the other, you get the same message. All right. So you remember when you have a directed graph where you have, even though it is a tree-like, when you transform it to an undirected graph, you have to marry the parents. So if you have two parents, basically the undirected graph is going to have loops. Okay? So one easy way to get away from this problem without using this concept of loopy belief propagation is to transform this graph to what is called a factor graph. Okay, and it's an idea basically not everybody is using. It's sort of a construct, that allows you to extend the SumProduct algorithm to Polytrees. So what I'm going to do is I'm going to review this and tell you how this algorithm is going to work for these factor graphs. So we have to spend maybe 10-15 minutes to discuss what's a factor graph. So in a factor graph, in addition to the nodes that denote random variables like x1, x2, x3, you also have squared nodes that denote functions, potentials. So basically the factor graph is sort of is a graph that explicitly shows you the potentials that are used in the factorization of the joint probability distribution. So for example, let's look at this undirected graph, right? So I have P of x1, P of x2, they have no parents, times P of x3 given x1 and x2. So a factor graph looks like what you see here, okay? This is a function which is P of x1. This is a function which is P of x2. You notice these functions are connected to the nodes indicating which arguments are inside those functions. So P of x1 it's only involves x1, so it's only connected to x1. P of x2 is only connected to x2. And then we have this function of P of x3 given x1 and x2, so it's a function of 3 arguments. So this is connected to the 3 variables. Okay? So these are the variables, the random variables. These are these factors. And 2 nodes in the context of what we define a neighborhood in directed or undirected graph. 2 nodes here are neighbors if they're basically sharing a factor node, if they are parts of the same function, basically. So for example, x1 and x2 are neighbors because they're part of this factor node that connects x1, x2, and x3. All right. So a few more examples. So this is the problem that we just discussed, all right? I want to show you on this slide that the design of a factor graph from a given directed graph is not a unique construct. So you can have actually multiple factor graphs, okay? And nothing really to worry, at least in the context of this class. So for example, here, remember we had a factor for x1, a factor for x2, right? And a factor that involves the 3 arguments. Here, what I do is I only use one factor because this factor involves the 3 arguments. I put those 2, P of x1 and P of x2 as part of the bigger factor that involves all 3 together. All right? So this is one construct. This is what we saw before, right? The same. So these 2 are different, okay? Now, in this case, I suppose the cost of doing inference or something like this or something like that, it's practically the same because you notice here, you have 3 variables and here you have 3 variables. So that is what defines the complexity of the problem. But if somehow you pluralize this with factors that have only, let's say, 2 arguments, that would be the best way. But you cannot do it here because one of the probabilities is of x3 given x1 and x2, so you need a factor that involves all 3 arguments. Again, variable nodes, these are factor nodes, they're functions. All right? So for example, in this case, right? So let's look. So before we had the directed graph, here we have an undirected graph. So we have a clique that involves nodes 1 and 2. So there is a potential of x1 and x2. And then we have a clique involves 2, 3, and 4. So we have a potential of 3 variables. So the factor graph is very simple. There is a factor there that connects x1 and x2. That's explicitly this function. And then there is another factor that connects 2, 3, and 4. Right, and as I said, there are several factor graphs that correspond to the same undirected graph. So in this case, there is only one click, so you can connect all x1, x2, x3 together in one factor. But here, actually, you can do weird things and split it in a factor of 3 and also a factor of 2. So, of course, you're not going to gain anything with that, but that's another story. So, look at this undirected graph, all right? And look at this factor graph and this factor graph, and don't read what it says there, which is computationally better to work with. Don't read this, okay? I don't have time to go and make animations on the slides, right? Life is already complicated making the slides. So which of these factor graphs do you think is computationally going to be easier to work with for inference? This or that, and why? This would be the easiest? Who said that, Nick? All right, I'm sorry to hear that. Now you're so famous, around the world, all the Chinese saying, who is that guy, Nick? So maybe we should turn the camera. All right, so why this is not the best option? I mean, when you compare the two, right, what is different in the two factor graphs? Here, this factor involves how many nodes? 3. So let's say each of these variables has k values, so it's k cubed complexity. Each factor here involves how many nodes? 2, so the complexity is k squared. Now, if k is very small, right, it will not make a difference. For example, if k is equal to, 5, no big difference, but, if this is part, you have this in a much bigger graph, of course, this will make a huge difference. This goes with k squared, this goes with k cubed, all right? So, all right. So let's just do one final example, and we'll leave it there. So this is a directed graph, okay? And this is sort of, it's an ugly construct. I think I believe most probably I did this on my own here, so it doesn't look very good. But let's look at all the factors, right? So x1 has no parents, so we need to have a factor that represents p of x1, okay? x2 has no parents, so we need to have a factor that represents p of x2. Now we have p of x3 given x1, all right? What is that? No, I'm sorry, p of x3 given x1 and x2. So that's this factor, so it connects x1 and x2. You see that? Right? It needs to connect basically x1, x2, and x3, all right? Let's see what else we have. We have p of x5 given x1 and x3. x5, x1 and x3, that's this factor. And then we have x4 given x2 and x3, and that's this factor. Okay? All right. This is an esoteric example, but it's an important example, but I will bypass it. So if you have questions, just ask me. Okay. So why we're interested to use factor graphs? Because if we have a directed graph that has here two parents and we moralize it and we get loops, but somehow we can transform the situation here with loops to literally to a tree graph. And if it is a tree graph, then we can do the SumProduct algorithm on a factor graph. All right, that would be a new algorithm. Okay, so does this look like a tree to you? All right, so here I have 3 nodes. All right, 3 nodes. Here, because I had these 2 single potentials, you can put those 2 single potentials there. Then here you have 3 nodes, and let me see, and and I suppose this doesn't hurt. I don't know from where it's coming. Another single potential there. Okay, so is this looking like a tree to you? I mean, can you remember there's a single path from any node to any other node, but here we're not looking only at the variable nodes, but we incorporate also the factor nodes. So if factor nodes and variable nodes, if you think of them as just different sets of nodes, this is a tree, okay? So the question is how can we do sort of inference and how we can extend the SumProduct algorithm on this factor tree. All right, that's another example of that we make into a tree, okay? So let's discuss what the algorithm is going to look like. So the only thing I am going to need right now is the decomposition of the joint distribution as a product of factors. And this will be my squared nodes, basically, each of these factors in principle, okay? So here is a decomposition of the joint distribution, and you notice I have factor FA, which involves two variables, FB, two variables, FC, two variables, and FD alone. This is actually what is called a bipartite factor graph, okay? You notice there are no connections between x1, x2, or x2, x3, or between FA, FB, FC, etc. So, all right. Don't really need this. Don't really need this. I am going to bypass all of this. And all right, so we need to discuss how we're going to do inference on factor graphs. It's going to get conceptually complicated, right? So you need to get used to visualize as to what is going on and what the definition of the message is all about, okay? And so let's say that somehow we have a node X, and you notice this node X is unbold here, and we need to compute the marginal of X, okay? So in principle, this is basically integrating out all the other variables but little x, okay, the unbolded X. All right, so I am writing now the joint distribution of all the variables X as this product that you see here, but let's clearly define what the notation is. So this node X here is surrounded by factors, because you remember every node is connected to one or more factors, okay? So I am looking now to this factor Fs, all right? Now think, if you take this tree and you put X on the top, it is a tree, right? So all of this part is going to be hanging down as one tree, all right? And that tree originates from the factor Fs, because simply this is a tree, all right? So can we look at this equation, and before I go to the next slide, tell me what is this function they are going to be like? What is it? You don't have to give me an equation, but looking at, so it says here, the joint distribution of all the x's is the product of these functions with subscript s for all s's that are neighbors of x. So for all factors that they are neighbors of x. So this factor and that factor and that factor, etc. And you remember, if you look at that factor, you get one tree. If you look at this factor, another tree. If you look at that, another, this tree. So what do you think is f subscript of s? Little x, comma, capital X, s. So you will agree with me, right? So this is a factor of s. This node will be connected to another factor, which will be connected to another node with other factors, etc. And each factor comes with its potentials. So when I say f subscript of s, little x, this is the unbolded x, comma, xs. What is that? First, what is xs, you think? Capital XS. They are a collection of nodes. Which nodes? On the subtree that originates basically on the factor Fs. So all the nodes that you have over there, I call them XS, okay? little x, it is there to remind me that I am looking at factors that are connected with x. I need to be able to define what, when I say s, right, s is a factor that is a neighbor of x. So I need to have the little x there. This is an unbounded x, okay? And what do you think it is capital F subscript s? What is involved on this thing? I mean, we said, right? So here is, this node, and this node is connected to a factor, which is connected to another node, and a factor, and again, this node a factor, to other nodes and a factor. So what do you think this F subscript S is? It is all the product of all the potentials, right, of all the factors on the subtree that originates from this factor Fs. Right? You're going to have a lot of factors on this subtree, all right? So the product of all of those will denote F subscript of S. So do not confuse this with this factor, because this factor involves only the potential that has this node, and that node, but there is node here, there is node there, there is node there, etc. Okay? And there are more factors. But the whole idea is that this whole thing is a subtree. All right? Okay. Obviously, if this is not a tree, right, you won't be able to do this. Okay, so we need to pay attention here, so I know what I'm talking. So XS denotes the set of all variables in the subtree connected to the variable node X via the factor node Fs, and this represents the product of all the factors in the group associated with factor Fs. Okay, this is what we just said. Now, I am going to, remember I'm interested, let's say, that's why I isolated this little node X. I'm interested in the marginal effects, all right? So if you want in the marginal effects, what do you need to do so this is your factorization. It's a nice way to factorize the joint distribution. If I only need the marginal at this node, what do I need to do? I need to integrate out which variables? All of these variables, capital of X, S, for all S, right? So basically, for every tree that originates from these factors Fs that they are neighbors of little x, I need to integrate the nodes affiliated with those subtrees. So what do I need to do? So I have the product of these functions. I need to sum. Each product has its own nodes, all right? So I can bring the sum inside. SumProduct Algorithm, you got the idea here. So I need to integrate this excess out. And this summation, where I have integrated all of these variables out, I define it to be the message coming from the factor Fs to node little x. It's a definition. So what is this message? Really, it is it originates from the product of all of these potentials where I have integrated out all the variables Xs. And the only variable that is left is the variable little x. So I define this. So basically what this says is that the marginal of the little node x is the product of all the messages arriving from the factors that are neighbors to little x. Okay? So basically, to compute the marginal of x, what you need to do is eliminate all the variables here and compute the message that comes from this factor to this node, eliminate all the variables up there and compute this message and then that message. The product of these messages basically gives you the marginal P of little x. And again, don't confuse, the bold x is all the variables and bold x is this particular variable. So the definition here is the message from Fs flex is the product of all of the factors affiliated with the subtree, where all the variables xs have been integrated out except little x. Okay? Makes sense? I mean, this is the elimination algorithm, right? We need to eliminate. So what we do is we eliminate in each subtree affiliated with each factor that neighbors node x, okay? And we can do this elimination here separately because once you hang this from little x, this is 1, 3. So you can eliminate the excesses, and you can do the same there, all right? And this is the message that comes from a factor to a node x. So it's a weird concept, right? Because this is a variable node, and before we were talking about messages between variables, but now we talk about a message that is propagated from a factor node, which is a function, to a node. And again, it's weird, but it's not weird once you know what the definition is, what it implies. I mean, this is a graphical construct, but really what it implies is take the product of all the factors here and integrate out xs. That's it. Okay, and we baptize this to the message that comes from a factor node to a variable node. Okay? Of course, you may ask me, are there going to be any messages from a node to a factor? Of course, there need to be some, right? I mean, otherwise, we're not going to be able to make a lot of sense. So let's see what is further going on here. All right. So we define this, okay. Now we need to define the message that goes from a factor to a node. Okay? The message that goes from a factor to a node. Okay? And any ideas what that will exactly mean? Obviously, if you're going to need a message from this factor to this node, all right, you need to get rid of everything here. All right? You need to eliminate all these variables. And to eliminate these variables, what type of potentials are being involved? Remember, this is a potential that connects, let's say, node x1, x2, whatever xm. This is just for demonstration purposes. And there is the little node x that's a neighbor of fs, and I want to find the message that this factor node sends to little x. This factor is a function. Will you agree this is a function? All right? So this is a function. What do you think is GM of XM, XSM based on what we discussed, with a similar notation we discussed for a factor before, with a tree affiliated with a factor. So what do you think? So here I need to account for all the potentials, right, involved on this subtree, and the only thing I have is this factor and the node that is being connected. So I have to account for whatever comes with each node. So what do you think is GM of XM, XSM? In simple words. Will be the product of what? I mean, I see this node XM, right? That is one of the nodes connected with fs, except x. So this would be what? Obviously, here there must be a tree, right? So the fact that I denoted as GM, XM, and then capital X, SM, the notation looks to me similar to what we had before. So what do you think it is? So what does subscript M? XM means basically that I'm looking on the subtree affiliated with node XM. What is capital of XSM? This is the set of all the nodes involved on that subtree. And why do I put the subscript S there? To remind myself that this node XM is a neighbor of fs, because I'm interested to figure out what is the message the factor fs sends to node x. So I need to know that I'm only looking at the nodes XM that are connected with the factor fs. Okay? So can you guess, looking, so I'm going to have, I'm going to have something like that basically, okay? You remember before we had, we had this potentials affiliated with a factor S, right? So can I write this like that now, explicitly? Basically before, right, we took everything affiliated with a factor Fs, all right? But now sort of I reveal these nodes x1, xm, etc. So I can write it sort of a little bit differently. So this is exactly what we had before. This is this, all right? Now what I do is I write it as the factor Fs times g of xm, g of x capital M, etc. It's the same entity. Before again, look, I was looking on the product of all the factors affiliated with this sub 3. So now, what I want to do is, I want to write this explicitly by having the Fs out, so I have to account for that, times the product of these G products of factors affiliated with the subtrees that are connected to each of the nodes x little m to x capital M. Are you getting a headache? No? All right? It's on a tree. And with each subtree, right, the product of all these functions. So this is a different way of writing it. So, so effectively, if you're interested to compute the message from this factor to the node x, what you have to do is, in that expression that I have to do is, you have to integrate out the variables x1, xm, right? Because, this is what I have. But also you have to integrate out all the variables affiliated with each of these subtrees, which are, should have put actually an S there. Okay, it's all right. So we have to integrate those variables out as well. Okay? So, before we had this times this product, and now I have to integrate all the variables but little x to find the message that this factor sends to x. So the product of x1 to xm has to be outside because this is a function of x1 and xm. And here I have to integrate out all of these variables xsm affiliated with this subtree that hangs out of node xm. And this is what this thing does. So if you look carefully on, again, similar to the definition we gave before, here what we do is we're eliminating all of these variables xsm. So imagine you do elimination, variable elimination, you get rid of anything below. So what is left is the message that goes from this subtree to the factor Fs. Because everything else you eliminate it. So effectively what you have is, you have that the message from Fs to x is summation on all of these variables of the factor Fs times the product of all the incoming messages from the nodes x little m to x capital M to the factor Fs. Usually, you can actually see this easily, right? So the message that goes out from here to there is this factor times all the messages coming from this node to this factor, all right? And this message, remember, came by eliminating these factors on each of these terms, okay? So, and then of course, when you multiply this, so this factor times these messages, you have to integrate the variables x little m to x capital M out. So what is left is a function of little x, and that's the message from a factor x to a variable node little x. Makes a little bit of sense? Again, you know what? The way to say it is sort of graphical, right? And if usually you write something that's out of common sense, you cannot go wrong, okay? So the message from this, from Fs to x, is this factor times all the incoming messages to this factor, and then you have to get rid, basically, because each of these messages is a function of these nodes, so you have to integrate all of these nodes out. Okay? And again, you may say, again, what are these messages? These are the messages once you eliminate everything past those particular nodes. All right? So, what we have is, so let me go back to the two equations, all right? So here we have an equation, well, I don't want this one, actually. Okay, it doesn't matter what I was looking. So we basically discussed the way to propagate messages from a factor to a node, and then from a node to a factor, okay? Right? So actually, I'm sorry, from a node to a factor, let me just go back to this, okay? So if you want to find the message, okay, from XM to FS, all right? So from a node to a factor, do you agree with me? This is the operation we did, right? We eliminated, on this sub 3, we eliminated these variables. This is our definition, 3 lines there, all right? When we get rid of all the variables but XM, we get basically the message from XM to the factor FS, okay? And you can write this explicitly as the product of all the factor functions affiliated with this sub 3 M there, of all the factors but the factor Fs, because you are interested to figure out what is the message this node sends to Fs. So you're not going to count the message Fs sends to the node, right? So here is the product of all these functions, if you like, except the ones that are coming from the factor Fs. So effectively, to compute the messages from a node to a factor, what do you have to do? So this is a node, and you want to find the message that this node sends to a factor. Take all the messages that all the neighbors of this node, except this factor, send it to this node, and then propagate it. So basically, the message XM sends to Fs is the product of this message here, and that message, and that message. And of course, you don't account the message to Fs. You don't want to send to Fs what's sent to you. A little bit of sense? So basically, you can see sort of the elimination algorithm for trees in action, where you know it's all you can do this simply because these are trees. So if you hand it from anywhere, you basically get a subtree, and you need to understand only 2 relations. The relation that you see on the top, which is the message a factor node sends to X, to any node X. Very easy. Take the factor function, all the messages arriving to the factor from its neighbor nodes except this little x, and integrate all the variables out but little x. And then similarly, if you want a message that a node sends to a factor, take all of its neighbor factors, compute the message they send to him, and basically that will be the message you can propagate to Fs. Boundary conditions, because at the end of the day, you will either, when you apply this, you'll be either at the leaves or you will be at the root. So if it happens that this is the leaf node and it's a variable node, then the message X sends to the first factor, you set it equal to 1. All right? So this is very essential. If it happens actually that in your factor graph, the leaf node is a factor, then the message that you send to the first node connected to this factor is the function f of x. Okay? So we're going to do shortly some examples. And I think even if you program this for your for your next homework, I would suggest in some of these examples you try to do things by hand to convince yourselves that the algebra does make sense. Okay, so before I start showing you some examples, let me just say that in principle, you don't even have to bother to discuss about messages sent by nodes to factors. I mean, in principle, you can see the whole algorithm, the SumProduct algorithm for factor graphs, as messages sent from factors to factors. Because, for example, you may say, but I need the message that to compute this blue message, I need to know the message this node sends to this factor so I can multiply it with this message. Yes, I know that, but the message that this node sends to this factor is what message? Is the message that this factor sends to this node. So you can go directly from messages factors send to these nodes and to these nodes that they are neighbors of fs, and then multiply all this together to get the blue message from this factor to the node. Okay? So you can bypass, basically, if you want, the need of having, messages from nodes to factors and factors to nodes. Now, I know this is a little bit, it's not actually, this is a very easy example, all right? So actually, we're gonna, this thing with chains, actually this is not a state space model, it's a chain. So actually, I feel good, we can do this problem, all right? So imagine you have a Markov chain, okay? So this is state xn minus 1, this is xn, this is xn plus 1. And let's say the only thing we prescribe is the dynamics of the chain. We say basically, what's the probability of xn given xn minus 1? This is Markovian. What's the probability of xn plus 1 given xn? And now what I'm going to do is I want to basically pose this elimination algorithm, the SumProduct algorithm, as SumProduct algorithm in a factor graph. So I'm going to take the Markov chain and transform it to a factor graph. All right? It's very weird to do this because the problem is trivial, but on the other hand, sort of very instructive. So everybody knows what the Markov model is, right? You have this node, and where you're going to be next depends where you were before. Okay? So these are the nodes. So what are these, I don't know what color is that, yellow or whatever. What are those square boxes now? The factors. So what is this factor accounting? This factor, let's say. This is the probability, effectively, of the transition from xn minus 1 to xn. All right? And this is the probability of transition from xn plus 1, from xn to xn plus 1, etc. Okay? So these are the factor nodes. So let's say that somehow we're going to apply this rules I gave you for sending messages from a factor to a node and from a node to a factor on this chain to see if things make sense. Okay? So, we did not, I think, prove it, but it's actually it's already in the slides that we just passed, right? If you want to compute the marginal of any node, remember, a node is connected to a factor here and a factor behind you. You don't have two nodes connected with each other as a factor, right? So, if you want to find the marginal at a node, it is basically the product of the messages the factor, let's say, n minus 1 sends to node n, and the factor n sends to the node xn. So let's see this graphically. If you want to find the marginal of this node, is effectively the product of this message and the product of that message. You remember in a regular graph, right? How do you calculate marginals? You take the messages coming from the left and the right on a chain. So here, on the left is a factor node sending a message. On the right is another factor node sending a message. All right, so I'm going to take this as a given, and I'm going to see how this looks like, to see if we can recognize if it gives us anything familiar. So this is the factor. So we're looking here, right? So this is the factor, this factor, all right? Don't pay attention to this summation. Is this message there equal to this summation, and from where is that coming? With words. Basically, this is the message from this factor to this node. To compute that message, what do you need to do? From a factor to a node, what do you need to do? Pay take the factor himself, multiply with the incoming message, and then integrate out all the variables but xn. And because this is a Markov model, integrate out xn minus 1. So what you do is take the factor, which is this n minus 1 n, that's the conditional probability really, okay, times the message that comes from the node xn minus 1 to this factor fn minus 1 comma n. Yes? All right? And similarly, I want to find the message from this factor to this node. That is again this factor, right, which is this, times the incoming message from node xn plus 1 to this factor, and then you have to integrate out xn plus 1, so at the end of the day, everything is only a function of xn. Okay? So, now, will you agree with me that this message here is the same as that message? Is that the case? No, wait a second, what I'm going to say, sorry. Do you agree with me now? I see this. So we calculated this, right, as this factor times, we calculated this message as this factor times this message, and we integrated out xn minus 1. So let's look now at this incoming message, which is from node xn minus 1 to this factor. Will you agree that this message is the same as that message? Because in that way I want to see these messages as messages from factors, basically, all right? So there's no potential here or anything like that. So this message is the same as that message. So what I have done here, I substitute this message as the message coming from a factor fn minus 2 to a node basically n minus 1, okay? And similarly, I took this message to be the same as that message, all right? And I write like that. So now I give names to these messages, and I call this the alpha message, and I call this the beta message. So the alpha message is computed from left to right, forward calculation. You can see this. You know, to calculate, there is a recursive relation here. If I call this m alpha at xn minus 1, you know what this whole thing is? What name should I give to this whole term there? It's the forward message m alpha at xn. And this, if I call this m beta xn plus 1, all right, xn plus 1, this whole thing, what it is m beta xn, is the message coming to xn backwards. Did we do that problem for a chain, the forward and the backward messages? So basically, what you do here is you are recovering, if you like, the marginal of xn as the forward alpha message, which is what you see here written recursively, and the backwards beta message, which is what you see here recursively. I mean, you haven't really learned anything new in this example, but I wanted to just simply show with this rather intensive graph that the algorithm does what it's supposed to do, and what it's supposed to do for chains is basically to compute this xn with a forward message propagation and a backward message propagation, and then you multiply the alpha and beta messages and get P of xn. And similarly, you can multiply the corresponding alpha messages to get the marginal of this node and of this node and everywhere else in the graph. And, okay? And obviously, to start this algorithm, right, so you need to use the boundary conditions that I indicated before, and we have done this for the alpha and beta messages. So if you take this recursive relation that I had before, so if you want the message that leaves node x1 to go to the first factor, basically what you need to do is integrate x1 from the potential psi1 to the first two nodes, and the message from the first node to the first factor. And we set to take this equal to 1. So you notice the first message that comes is nothing else but marginalization in x1 of the potential between nodes 1 and 2. You really have to sort of spend some time doing this, and actually not spend some time doing this, program this. Okay, because sort of looking at it, this is, a chain, right? So this is the most trivial case. If we try to do this, and we're supposed to do this in 2 days or 3 days on 2 or 3 lectures on state space models, so we connect observations of the states also, you will see that things may get a little bit more noisy, okay? But bottom line is you have messages that result from variable elimination, and in a factor graph these messages are messages from factors to nodes or from nodes to factors, okay? Once these messages are being computed, you can evaluate anything you wish. You can find marginals, you can find conditionals, you can put evidence in the model, join distributions, etc., etc. All right, so let's take a break, and you guys will help me to do not a chain, but a little bit more interesting problem. Still a toy problem. So we have 4 nodes, and we have 3 factors. That this factor connects nodes x1, x2, so function of x1, x2, function of x2, x3, and function of x2, x4. So tell me what do we do? Let's say, let me see what it says. I mean, let's suppose we want to compute all the marginal distributions in this graph. And evidence is not an issue. You just use slices of these distributions if you have evidence, but let's say we want to find the marginals of x1, x2, x3, x4 in this graph. So using the this SumProduct algorithm on factor graphs, what do we need to start doing? What would be step 1? Choose a root node, and can be anything. Doesn't really matter, okay? So in this case, let's say we take the root node to be x1, all right? So you're going to start sending messages from root node to this factor, then from this factor to this node, okay? Obviously, to send from this node to this factor, you need to know what is coming from below. So you're going to have to send a message from x4 to this factor, compute this message, then multiply these messages, you get that. Then integrate this thing out through this factor, and then you get the message to x3, and then start going backwards. All right? So let's look at the calculations one at a time. Equation 1 says the message from x1 to fa is 1. Why is that? I know, but we said it's a boundary condition, right? It's the boundary condition for this problem, and it's because the root here is a variable node. It's not a factor, okay? And we will do something with a factor maybe in another example. So from x1 to fa, this message is equal to 1. Now from fa to x2, what do we have to find this? We have to take the factor, multiply it with what? With the incoming message, which is how much? 1, and then get rid of x1. So if I wanted to write this sort of explicitly, I would say inside the summation times 1, right? But you get that. Okay? So then let's see, we are stuck here because we need to compute things from below. So we have to find the message from x4 to fc. That's also a boundary condition. Okay? So the message is 1. The message that fc sends to x2, I have to eliminate x4. The same way we do elimination, so you get that. And now we are ready to send a message from x2 to fb. So the message is basically the product of the message FA sends to X2 and FC sends to X2. So basically the message from X2 to FB is the product of FA to X2 and FC to X2. Okay? And then the message from FB to X3 is the factor FB, right, times this message, and then X2 integrated out. I mean, really, you can sort of do this graphically. You don't have to remember any complicated expressions, right? So every time you have a factor, what you need to remember is you have to multiply with a factor whatever incoming messages you have, and then you integrate all the variables except the target variable. Okay? All right? So we're not done now. We went one way, and you remember to get sort of marginals, you have to know in every edge what comes in and what goes in both directions of the edges of the graph. So now we have to start sending a message from X3 to FB, 1, from FB to X2, a factor again times 1 and integrate X3 out. Now let's see what's going on. We're going to start sending from X2 to FA. Can I send a message from X2 to FA? Don't look at the equations. Am I ready to send a message from X2 to FA? What do we need to know to send a message from X2 to FA? We need to know what message comes in this way, which we computed, but also we need to know what message comes from the factor FC to X2. And that message was computed from where? From FC to X2 was computed in the forward step. Don't omit this. I mean, this message already, the forward message have already been calculated, so now you have to account for it. In this graph, in the message from X2 to FB. Yes, because so this is a variable node, right? There's no function involved with that. Let me see. Because let's see. You notice the message from FC to X2. FC to X2. It's. Oh, I'm sorry. This was eliminated. From X2 to. Oh, yeah. Good point you're making. So what is this supposed to be? So the message, let's see again, from FA to X2, all right, will be a function of X2. The message from FC to X2 will be X2. So this is corrected, okay? This is X2 there, okay? Thank you. Remind me if you don't see it corrected by tomorrow morning. Okay, all right. Did I correct on this slide? What was the message? X2 to FB. Oh, wait a second. Where is X2 to FB? Do we have this anywhere here? We're good? All right, okay. So basically, to find this message, right, we have to multiply the message from FB to X2, and then the message from FC to X2, okay? Then, to find the message from we have to find the message from X2 to FC also, going downwards, right, this message there. So that would be again, this incoming message from FB to X2, but also the message from FA to X2 we computed on the previous slide, all right, which is this message, okay? And of course, if you want to find the message from FC to X4, there is a factor involved, so you have to multiply with a factor FC times the incoming message from X2 to FC, and then integrate X2 out. Okay? So basically, this propagation of the message between from factors to nodes and nodes to factors is the same, but when you are basically sort of working with factors and eliminating factors in principle, you have to multiply with a factor function. Okay? I mean, you want to eliminate variables here, but the idea is, there is a function involved, and that function needs to be accounted explicitly. So in here, you don't have any factors, so it's basically the product of the messages. Here is the factor, and whatever product of messages you have, and then elimination of variables. All right, so just to show you that actually this, you can do lots of tests of your own, right? So let's say we want to compute the marginal effects too, right? So here is, based on what we said, if you want the marginal of any node, this means by the way I normalized this curly thing. I don't know if it shows, lots of the symbols may not come properly on the PDF, so if you see that, please let me know. So if you want the probability at x2, you have to take the message from FA to x2, FB to x2, FC to x2, which is this. And let's say, for example, if you want the message from FA to x2, FA to x2 is FA with x1 integrated out, all right? FA with x1 integrated out. Similarly, this is this with x3 integrated, x4 integrated. So I can write a summation like that. And actually, this is the join where I have integrated out all the variables but x2. So obviously, that's the marginal. I mean, it's a test, basically, to show you that things are really working properly. So, when you do problems like that, right, you may want to just go and do some trivial test to see that you haven't omitted sort of any information. And this, for this trivial example, you can see immediately that this equation, that is product of incoming messages to node x2, all right, indeed gives you the marginal of node x2. All right, I don't know if there is anything new on this example, so I'm going to omit it. Oh, actually, maybe we should do this example just for a difference. So in this example, the only thing that is different is I give you evidence that x1 is equal to a. All right, and you notice the elimination algorithm, right? Like we did before. It's practically identical. The only difference is that you basically have to propagate the information that x1 is equal to a, and the way you do this is by sending a delta function from x1 to f1. And you can immediately see that this works because if you want the message f1 sends to x2, this will be the factor f1 of x1 and x2 times the incoming message, and you notice when you integrate or sum this, it basically forces x1 to take the value a, right? This is the only thing you need to do to account for evidence. So if you have a homework problem for this evidence, there's nothing really particular that is needed. This already takes care of that. I have a lot of very simple sort of calculations that I want you to actually look at these equations and be sure that you fully understand, because here, you say summation, product, this and that. It's like, what is that? Well, I mean, it's very simple. It's all related with this tree structure and the factors we have on defined over the trees. But what I wanted here to prove for you was in 2 lines that if somehow you're interested to compute the marginal of all the nodes affiliated with one factor. So if you have a factor and it's connected, let's say, to 3 or 4 nodes, and you want the marginal, look how easy the calculation looks like. Take the factor corresponding to all these variables and multiply with all the incoming nodes that they are neighbors of the factor. So again, let's say if I had a factor with 2 nodes, right? It says take that factor, which is this, and take now the product of, so this is, 2 variables, take the product from all the neighbors nodes of this factor Fs and multiply these messages coming in. Okay, and the proof is basically given in one line by using this concept of, again, of variable elimination. And again, you know, let's see this is, if this makes sense. If you want, let's say here, to find the marginal of nodes x1 and x2, just to convince you that this is correct. So based on the thing that I proved here, and you guys should read, if you want the marginal of x1 and x2, it would be the factor. The message that comes to the factor fa from x1, the factor the message that comes from node x2 to fa, which is that, and the message from x1 to fa is equal to how much? It's similar to what we did in the examples before. How much is this message? 1, right? That's a boundary condition, and the message coming from x2 to fa, the message coming from x2 to fa, this gets interesting now, right? From x2 to fa would be the message coming from this factor to this node, and from this factor to that node. So it would be the message from fb to x2, and the message from fc to x2. And what is the message coming from fb to x2? All right, what's the message coming? Is the factor times the message coming from x3 to this factor, which is how much? 1. So you get this summation times that summation, and if I put those outside, you basically have to integrate all variables but 3 and 4. Obviously, that will give you the marginal p of x1 and x2. Again, you're not doing all of these things to prove this, right? But this is sort of, somehow it works. It's, you know, okay? You can actually, if you want the marginals of variables that they are not even connected through a factor node, you can calculate that easily as well. So you can read this slide, okay? And, well, and actually, you know, I think maybe I already applied this. You know, if you, so if you imagine that you have a node xi and there is a factor next to it, right? If you want to find the marginal of node xi, one trivial way to do it is to actually, on the edge between the factor fs and the node xi, take the product of the two messages in both directions. So if I have a node and it's connected to a factor and I want the margin of that node, take the message this way times the message that way, that will actually give me the marginal. Very nice sort of quick result in computing marginals. But again, what I want you to sort of appreciate is forward and backward messages, right? That's a universal thing in all of this type of calculations, right? You need to be able to propagate evidence from the leaves to the root, and then a downwards evidence from the root to the leaves, and only then you can compute whatever you're interested in, do inference and other tasks. All right. There is really nothing on the remaining of the slides except sort of summary of the algorithm that we just discussed on factor graphs. And what I have done here is I have used the notation from Jordan's reprint that I sent you once upon a time. And what he does is, to emphasize basically the different sort of type of messages we have, he uses the symbols mu to indicate messages from variables to factors, and then he uses the symbol mu for messages from factors to variables, and basically the update formulas are the same as what we have seen already in the lecture. So if you want, you know, for example, if you want to find the message from a factor to a node, you have to take the factor itself, all the messages coming from all the nodes, which are new messages, and then to integrate all of these variables out, except variable xi, and this will give you this, and similarly this, the message from a node to a factor, you have to find the product of all the messages coming from all other factors, except this one, that they are neighbors of xi, multiply them, and that will do the job. So the algorithm, it is a copy carbon of the algorithm we have seen for trees, but the only thing that you see here is there is new collect, right? There is new distribute, new collect, and so because we have two sets of messages, both going from the leaves to the root and the root to the leaves, but apart from that, effectively, if you write an algorithm, you go to another algorithm, it's basically minimal work. All right, that's the algorithm, and there is another example. You read it, and we'll take it from there on what day is it? On Thursday. I keep forgetting, even I don't even remember the day today. All right, so I'll see you on Thursday. And there is a homework due because you were not interested to even get an extension or anything like that. So there's no extension.